Okay, so add this into your notes. All right, so the title for today is continuity. So we're going to look at ways in which functions could be continuous. So the topic of continuity is very important in calculus because everything we do has to be continuous, otherwise they don't work. So we have to define continuity. Anybody have a good definition for us? What is continuity as reference to like a function or a graph? What do you guys think? Yes.
A function that continues without stopping.
Yeah, just something that continues without stopping. So we're going to try to be more technical. So we need a technical term. And to define that, we actually think about different ways graphs and functions will not be continuous. So we start with thinking about discontinuity. So some ways graphs could be not continuous is something like this. You got a function, and then all of a sudden at C, there's nothing there. That caused a discontinuity. So this is where f of C or x equals C is not defined. Undefined. Okay, anybody can think of another way graphs could not be continuous? Yes?
A jump.
A jump. So we'll draw a jump. So at C, maybe it's going, and all of a sudden there's a jump. Okay, the jump discontinuity. Any other discontinuity? Yeah. An asymptote. We'll sketch in the asymptote at C. So asymptotes will cause, they could, and I'm just going to draw one example. I'll just do the one where maybe it's like that. We call this the unbounded behavior. When there's an asymptote at C, it causes the graph to go on forever, unbounded. It also causes a discontinuity. Okay, and then there is one more. Yeah. Does oscillation cause it to break? It oscillates, but it doesn't actually cause the graph to break. So that one won't count. It looks like this one. Well, actually, it looks like that one. Looks like number one, except there's a dot. Okay. So this is just, this one's defined, but point not at the discontinuity. Not really a specific name, just happens to look like that. So to create a technical term for continuity, we need to have some statements that get rid of all of these types of graphs. So let's define it here. AP is particularly technical about that term, continuity, because we said that calculus was about rates. And what happens if the function represents your rates and there's a discontinuity like that happen? In real life, you're driving, you have a speedometer, it's going at a certain rate, and if there was a discontinuity there, what do you think happens? You disappear, right? And that's not real life, so we need things to be continuous. So we need a strong definition. Okay, so this is like a glimpse where you, at that moment you disappear. Let's talk about number one. What is a statement that will say we can never have something that's looks like that? You just have to say the opposite of that, right? So we'll say that to be continuous, the function f of x must be defined. We'll just say must exist. For all x's. So no matter what x we use, it says we will have a y value. Does that take care of the discontinuity graph 1? Yeah, that means if that was the case, this will not be true. And so we're working our way towards that. But here's an example where everything is defined, but it's not continuous. So what's another statement that gets rid of this issue? All x values must have one y value. So that actually just fits this. All x's have one y value. So it doesn't really change it. Because right here at c, when c is x, we have a y value. But it doesn't say that there's, it doesn't get rid of the jump. A statement that will say there is no jump. How would you guys state that? Yes.
All points are defined.
All points are defined is just this.
Every x has a limit.
Every x has a limit. So add to that.
Every x we have one f of x.
I feel like you guys are all just stating the first one, that for every x there's a y. Yas has it. That's another statement. I'll reword Yas' statement and then we'll put the other statement as she's just said. So Yas said that basically he says the limit must exist. If the limit exists for all x's, C stands for all values, would we ever have this issue? The limit says as we approach C exists, so that actually forces this right side to go to a specific limit and the left to go to a specific limit. It gets rid of this issue. If the limit exists for all x's, does it get rid of this issue? This is also gone. So we took care of this, took care of this, took care of this, and then see if you guys could remember Eshi's response. How do we take care of this? You guys heard that. The value is here, the limit is there to get rid of this issue. Yeah. Say that louder.
The value and the limit.
Yeah, the value is just f of c. The value actually equals the limit as we approach c of f of x. And they equal the same thing, we'll call that L, a output L, where C and L are just variables for x's and y's. Okay, if I have those three conditions, none of these types of discontinuity will exist. I could make my statement that my equation is continuous. So that is our technical term to show that a function is continuous. If f of x exists for all x's, there is no undefined, so it gets rid of this one. The limit exists at all x's says that this side will always go, and then this side just starts right there. So no more jump, no more asymptotes. This is the last condition, is just to make sure this dot lands in there to make it a smooth, continuous curve. Okay, so AP Standard, they're really picky when they said use the definition of continuity or proof that something is continuous. They want you to show all three things. So you must remember your three steps, and then you write your conclusion. So we're going to try some examples like that. So the questions are just to use the definition of continuity to determine whether f of x is continuous. Sometimes they'll tell you the specific point of continuity that they want you to check. Sometimes you might just have to identify the possible place where it's not continuous. Most of the time, these are going to be piecewise functions. Piecewise functions are functions just composed piece by piece. So we'll start with some simple ones. Okay, so a piecewise function defines one function in certain interval. So this is the domain of your piecewise function. These are your equations. It says that when you go to graph this graph only shows the square root graph from 0 to 3. After that, it shows this one from 3 to 5. So there's a domain from 0 to 5. And from 0 to 3, it's this equation. And then from 3 to 5, it's this equation. So they want you to show algebraically that there's a connection there. So here's a picture. You don't have to draw this, but this might be a possibility. So right now, from 0 to 3, you have a square root curve, and let's say it looks like this. And then from 3 to 5, it's a line that's actually curving downwards. This means it's an open dot, since it's not included. And these means it ends and it's a closed dot. So right now your graph has a possibility to look like this. You're going to show that you're trying to check whether it looks like that or it looks like this. Where maybe the square root graph goes like that, and then the line actually attaches to it. So you're just trying to show that it's not continuous or it's continuous by using the definition of continuity. Okay, So then you start off. Ethan, first condition. Yes. Okay. All right. Yeah, f of x must exist for all x's. So right now, this one is a square root graph that's continuous everywhere, and this is a line that's continuous everywhere. The only place that's not has a possibility of not being continuous is at 3. So you just want to say that at x equals 3, there's a y value. So f of 3, you're saying, does f of 3 exist? Okay, so this next part's important. Now, don't write this yet. I'm just going to show you why this is wrong. Or actually, you guys tell me why this is wrong. Yeah.
It's not equal to that for the x value, it's not equal to
Yes. So your domain says you can only use 3 in this one. So if you show your work like that, you're using 3 into the second piecewise function, and this domain says you cannot use 3 there. So it's not defined here. So if you want to show that it exists, you must show that you plug it into the right equation. So we're really technical. Okay. Because 3 is defined on this only this equation, you plug into this one, you've shown that it exists. Okay, then we move on to the next one. Mia, what is the second condition of continuity? Okay, so the second thing is, will there be a jump discontinuity, or will the limit exist and it equals L, like this one? So to prove that, you actually have to go to your left and right limit to prove that the limit exists. So start off by saying, as we approach 3 from the left, which equation is the left equation? This top one or this bottom one? The top. So you must pick the top one. Take that one's limit with a direct substitution. We plug 3 in. It's 4. Square root of 4 is 2. Okay, we haven't proved that the limit exists yet. We just proved that the left side exists. Now let's talk about the right side. So we'll pick the right equation. Also do that one's limit with a direct substitution. We get 2. If the left limit is 2, the right limit is 2, then we write a stronger statement without the little plus or minus. And since there's 2 equations now, we don't pick one. We just say f of x. And we say it exists, and it's 2. So I prove that the value exists, the limit exists. 3 is just a restatement that you realize the value, f3, actually equals the limit, and they equal 2. The value equals the limit, it is 2. You finish your conclusion. Therefore, we know that our equation, f of x, is continuous. And that's it. So it ends up that it looks like that if you were to graph it. Okay, if any of those condition fails, then it automatically is not continuous. So 1, if you check the value doesn't exist, then you just stop and you say, well, the value doesn't exist, it's not continuous. 2, you check the limit, it doesn't exist, it's not continuous. 3, you compare your outputs and they happen to not be equal, so it's not continuous. So We'll try another one. We'll do another example, but this one we'll maybe do an example of not continuous. Okay, you guys have enough time to write that down? Okay, same question. So we're just going to check whether this piecewise function is continuous or not. Usually these are piecewise functions because if it's just a polynomial, all polynomials are continuous. So if you guys just have a polynomial like this quadratic, you don't have to use a definition because we know that it's continuous. You just state that this is a polynomial, it's continuous everywhere. This is also a polynomial of one term, it's continuous everywhere. There's a possibility of not continuous where? At one spot, at 2. So right now we're just concerned about, is it continuous at x equals 2? This is a line that's continuous everywhere. This is a quadratic that's continuous everywhere, but maybe at 2 they don't connect. Okay, so then we're just going to follow our approach. 1. Is there even a value at 2? Well, it's defined on this one. So we plug into that one. Yes, the value exists. 2. Does the limit exist? And does it equal each other? So we check the left first. The left is the top function. You know it's the left because x is less than 2. You plug in a direct substitution, you get -4. So far, so good? Then we check the right. Put a little power 2 here, indicating this is the right limit. The right limit is the quadratic, so we write the quadratic here. Direct substitution gets me 4. Maybe I'll do the math down here. Okay, this gives me -3. What does these two tell you? The limit does not exist. Or we could just say the limit does not exist. Yeah. Okay, the limit doesn't exist. We don't have to show step 3 anymore. We know that this one's not continuous. Because it just didn't exist. Okay, let's try another one. Let me pick a good one. Piecewise function. Actually, let's pick a absolute value one. Let's try this absolute value one. And the question is the same for all of this. Determine if f of x is continuous. Okay, so we have a function. There's a place where this function has a possibility of being not continuous. Where is it? Which x value? 10. So that's where we're going to check. 1, does the value exist? And if it does exist, what is it? at 10. Actually, let's see. I feel like when you guys get these, there's a little bit more information they want to give you because let me give you the boundaries. Or okay, let's think about it like this. So when you see absolute value function, they're treated like a piecewise function. Where the left function has a minus and the right function just has a plus. Yeah, I wanted to give you this part. So you see this, but you want to think about it like this. This is the way that you will get it to always be positive. So that absolute value part breaks up into one that's minus, one that is positive. Usually the minus one is less than that breaking point, and then the positive one is greater than. So depending on what we wrote down, f of 10 is what? 0 over 0 if you plug it into this one, but 0 over 0 says it's just, we don't know yet. So anytime it's 0 over 0, you guys do what to your equation? Yeah, it's already factored out. Simplified, it turns out to 1. So f of 10 actually is 1. If you guys were to plug it up here, would it be, what would it be? Yeah, it'll just be -1. So this one is kind of awkward, but any value you guys pick less than 10 is -1, and any value you pick greater than 10 ends up being +1. So if you plug any x in, that's what we get. So the value exists. 2, we're going to check if the limit exists. So we'll check the left limit as we approach 10 from the left. It's this one. That's the left one, but we know that since it's a 0 over 0 indeterminate, it actually simplifies to 1. So when we take a limit of a constant 1, we just get 1. Then we check the right limit, and that's this one. It does produce 0 over 0, but we're going to simplify. It turns out to be 1, so the limit from the right is 1. Oh, this is actually the same conclusion as example 2. The limit does not exist. So since it doesn't exist, f of x is not continuous. All right, we'll jump to a different type of question. I'll leave this up for a little bit longer. Okay, you guys done with this? Okay, maybe we'll try one that condition 3. Actually, do we need to do any more of these? Okay, you just have to check your conditions. Okay, it's a different type of problem. Sometimes they want you to find a particular value that makes oh, I need scratch paper. That makes your function continuous. So a different type of equation question now. Okay, this one you guys don't have to be technical with your definition. You are just looking for a particular value that makes your piecewise function continuous. So let's define our piecewise function this way. Let's make it a cubic, and let's just make it a quadratic, and an unknown a value appears. We are concerned at 2. So for this piecewise function, there's a possible breaking point at 2. And depending on the a value, it could be continuous or not. So here are some visuals. The cubic function looks like this. And it happens to end at 2. Right after the 2, this piecewise function tells us that a quadratic function starts. But the a is your stretch factor in your transformation. So if the a is a really big number, it's really skinny, and it maybe stretches your curve too high up, and it doesn't start there, so it causes a discontinuity. But what you want is you want a particular a that forces this one to actually get grafted and starts right there in that spot. So we're not as technical with these. We just need to solve for the a. And the picture kind of helps us out. If I want the second one to start right there, what are some things that must be true at x equals 2? Yeah.
It must be defined.
Must be defined. But to add to that, yeah, they have to have the same y value, so we could set them equal. If this one goes there, it ends, it has a particular y value. This one also needs to have a same y value at x equals 2. So we end up just setting the equations equal, letting x be 2, and solving for the unknown a. So if I let it be 2, when this one stops at 2, this one will start right there, it will connect. And it will make it continuous. Okay, we'll try another one. Maybe something like this. Okay, how about this time find the a and b value that make f of x continuous. So this next piecewise function will have an a and a b. So let's start with something like this. We'll say it's a constant 2 for all x's less than -1. and maybe there's a line that's between. It should start right after that one. Since I made that one less than or equal, this one will just be greater than. And maybe it stops at 3. After the 3, we'll make it 5. So new question. Let's talk about the visual of this right now. So here's what's happening. Left of this statement says left of -1, there is a function close dot. It's a constant 2. So anything left of this is 2. We'll go to the third statement. The third statement says that after 3, there's a horizontal one that's 5. So let's pretend that's 5 up there. And so our pieces, we need to find the A and the B that cause this line in the middle to connect those two. So let's say we guess a A and a B. If we just randomly guess an A and a B, we will be able to create a line, but it might be that. And we actually want it to appear here. So we need to find the right A and the B to get that line to line them up and connect them. Okay, so we're going to actually start right here in that spot. First, I need these two to connect. If they have to connect, what's the equation I could set this up as? If this has to equal that, the equations have to equal. These two equations must be equal to each other at x equals -1. So at -1, these two lines equal. I let x be -1. But then I get to here, 2 unknowns. I'm stuck. So I move on to the other piece. At x equals 3, these two have to equal. The middle one and the 5. So I let x be 3. But then I have 2 unknown. 2 equations with 2 unknown. How do we solve this? Yes, systems of equations. Okay, so we just have to do a system of equation, and then we should be able to find the A and B. Let's do elimination. Let's just put those on top of each other. And work our way to eliminate either the A or the B. So what do you guys want to eliminate? The B? Okay, let's eliminate the B by multiplying the top function by a negative. We are able to add straight down. B is eliminated. A is 3/4. To find B, I'll just pick one of these equations and substitute B or A back in. And solve for that. So it'll be 2 plus 3/4. (11/4). Okay, let me give you a visual of that. I'm going to log into Desmo. You don't have to, I'm just going to show you what our goal is. I'll put this back up. But this is the idea. So we had a constant function, y equals 2. And in Desmo, if I wanted to just be graphed from there, we get something like this. So we have a y equals 2. And in the middle, we have this unknown line, ax plus b. And that one is only from -1 to 3. So it's not going to sketch it yet because I haven't given it the a and b yet. And then the third function is a constant 5, and that one sketch from 3 onwards. Okay. So we have 2 lines here. And depending on my a and b, if I let a be 1 and b be a random, this is my guess. Maybe I'll need a negative or something. Where is my equation? Oh, it doesn't like these. Okay. Oh, did I need to make that, -1. Okay. So it starts this one ends at -1, this one starts at 3. If I randomly just pick an A and a B, it creates the middle line, but it doesn't connect. So then what we just saw for is we said that A has to be 3/4, and B has to be 11/2. Oh, 11/4. Oh, and did I type in something wrong? Plus. There you go. So if I put it in correct, it will actually cause this one to connect them, and it's now continuous. So we're looking for the right A and B. Otherwise, if we just do a guess, we'll get something that doesn't connect. So we wanted it to connect, and we're solving for the right. Okay, so this next part, I want you guys to try it. Find the A and B that makes this piecewise function continuous. How about I'll give you that one? Or let's see. I have some good examples, but I'm not organized and I don't know where it went. Where is my equation? We'll try. Oh, we'll try this one. Okay, so we'll do that one from x less than -1, and then let's toss a line in the middle. And then maybe right after that, we will put the 1/x graph there again. But we'll just look at it past the 1/2. So find the A and the B that makes it continuous. I'm going to do a rough sketch of this while you guys are doing your work. So 1 over x is a rational function. And it looks like that on this side and that on this side. But I actually don't see all of it. I see the 1 over x graph from there. And then the 1 over x graph appears over here again. But this time at 1/2. And it looks like that. So that's this half, and that's that half. This is telling me that I only see the 1 over x until -1, and then it stops. And then this third piecewise is saying I see the 1 over x after the 1/2. In the middle is a line. Your goal is to find the a and b that forces the line to connect, to make it continuous. If you find the wrong a and b, this line will not connect. Okay, I'll give you guys a couple minutes to find me the a and b, and then we'll put in Desmo to see if it's the correct a and b. Okay, while you guys are doing that, let me get it graphed so we can take a look at it. Okay, I'm going to randomly guess a and b to get us started. So on this half, until -1, I see the 1 over x graph. Now, if I didn't do that, this is what the 1 over x graph looks like. But the domain restriction on the piecewise says I only want to see that much. So let me just guess like a 1 and maybe a 3. That was not the right a and b. It didn't connect. It wasn't continuous. So you guys did the math. What did we get? Yes.
A equals 2, B equals 1.
A equals 2, B equals 1. Okay. So if A was 2 and B was 1, it connect. So that is your answer. Okay, we'll go back, show the work again, just to finish our notes off. But what you want to do is you want to look at this possible place of discontinuity. And you could say, well, right at x equals 1, these two equations must equal. And that's this one and this one. So you make them equal. You already know that x has to be -1, so you're just going to plug it in. And it gets you this much. Then you move on over here, and you know that at x equals 1/2, you got two equations, this one and that one, that must be equal. So then you set it equal, but you let x be 1/2. Oh, is it a positive 1/2? Yeah. So now you guys have a half a plus b equals 2. But it's two equations, so this means that we must do systems of equation. Do you guys want to do substitution here, or you guys just want to do elimination? Okay, if we do substitution, we'll just solve for one. I'm going to solve for b here. Okay, so b is that. Substitute it in. Should be able to find my a at this point. I got a half a and an a. Is that 3/2? Then I can move the 1. Multiply both sides by 2/3. A equals 2. Okay, once I get that a equals 2, I'm going to pick one, plug in, I'm going to pick this one, plug in 2, solve, and it happens to be 1. So since it's a nice number, you may have guessed the a and the b, but the previous one, 3/4 and 11/4, would you guys able to guess those? Test the a and b. So you will have to just solve the problems. Do we have time for one more? Yes? No? All right, we'll do one more, and this one we'll do a trig one because these are more technical. Okay, let's do 4 sine x over x, and then we'll do an a minus 2x. The question is find the a value that makes g of x continuous. Okay, so sine is oscillating. It gets to 0, and then this is just a line. The a actually plays the part of the vertical shift. So I'm thinking it looks something like this, and then sine stops, and then the line starts somewhere. And the goal is to not have the lines start anywhere, but to find the right a that the line actually starts where the sine curve stops and connects. Okay, so since this one is only two functions of this piecewise, all I have to do is set them equal at the breaking point 0. And then let x be 0. So then I get A equals, sine of 0 is 0, and that is 0. Okay, so what does that mean? Yes. That is inconclusive right now. Indeterminate. Yash?
Do you think the sine x over x would make that 1?
Sine x over x? Oh, sine x over x is not 1. What makes it 1?
Or is that a limit?
When there's a limit. As we approach 0 is 1. Okay, so I can't just say it's 1. It actually ends up, you can get away with it, and it is 1. But the technical piece now is a little bit different. This time, setting them equal to each other is not enough. What should you do to see the 1? This time, you might have to do your definition of continuity to try to find the A value. So, 1, since it's undeterminate, 1, we just have to make sure there actually is a value there. And we plug into the second equation, but what does that give us? Oh, we don't have we could plug into the second one, and we can plug into that one, but we're at that same spot. So maybe we're at the second condition. Let's check the limit. Okay, let's check the left limit. When we check the left limit, we know that we could take out the 4. And now all of this is what? Okay, now all of that is 1. And then we could check the right limit. The right limit is the a minus 2x. And we want that to be equal to what to make it continuous? 4. So that part we'll just fill in. Since we wanted it to be continuous, we'll say it also has to go to 4. So we need to solve this side. Direct substitution allows us to put the 0 there. That is saying that A must be 4. Okay, we could check by putting a 4 there and making sure that it exists. But I think we got our A, so we're fine.